black has always captivated physicists. Holes, for a prolonged period of time, have been a phenomenon that has intrigued scientists for over 100 years. These enormous entities, which pose a threat to the comprehension of gravity, have largely remained invisible to us. A black hole that is 2 to 4 million times heavier than the Sun is tremendously powerful. However, due to decades of research, our knowledge has evolved from nearly nothing to uncovering more details, sometimes in unexpected ways. A recent breakthrough has occurred, with researchers, including those at the Kaku Institute, announcing that they've been able to peer inside a black hole. This new data has revealed aspects of the universe that were previously missed. Let's delve deeper into black holes and explore the awe-inspiring space they inhabit. But before diving into the recent revelations, it's important to understand the fundamentals of black holes. Based on the idea of black holes, significant gaps in our comprehension still remain. The theoretical possibility of a black hole emerged in 1916, when Albert Einstein introduced his general theory of relativity, which suggested such objects could exist. Nevertheless, black holes remained speculative until the 1960s, when scientists first observed strong evidence pointing to their existence. While studying the binary star system Cygnus X1, astronomers discovered an unusually bright blue star emitting X-rays. This star was not a typical celestial body, it was orbiting a mysterious, massive object. Upon further investigation, it became evident that the X-rays weren't just floating in space, they were being drawn in that direction, indicating the presence of a black hole. This discovery was a major milestone, proving that black holes were not just theoretical ideas but tangible phenomena. The importance of this finding cannot be overstated, as it meant that an entirely new category of objects existed in space, requiring prompt and careful study. Researchers worldwide then focused their attention on black holes with renewed interest. The first confirmed black hole, Cygnus X1, is located around 6,000 light-years away in the Cygnus constellation. It is much brighter than our Sun and has an enormous pull, so strong that even light cannot escape it. This is why it is referred to as a black hole. The nature of a black hole is both fascinating and daunting. It denotes a region in space where the gravitational force is so powerful that nothing, no matter or light, can break free from its pull. Anything that comes too close to a black hole is inevitably sucked in and lost forever. This threat makes studying black holes both compelling and crucial. But does this mean we're in immediate danger from them? Despite the nearest black hole being about 500 light-years away, this distance still raises concerns about potential risks. However, the true scale of black holes is only just beginning to be understood. Following the discovery of Cygnus X1, astronomers began searching for more black holes. It's currently believed that there may be up to 100 million black holes in the Milky Way galaxy alone, though identifying them remains a difficult task. Estimates suggest that millions exist within our galaxy, demonstrating the significance of studying these enigmatic objects. The primary concern with black holes is their immense gravitational force. This pull is so strong that it draws in everything, including light. At its center, the black hole, known as the singularity, is where all the matter that falls into it is compacted into an infinitely dense point. In simpler terms, black holes act as cosmic vacuum cleaners, pulling in everything within their reach. If a person fell into a black hole, they would be stretched and compressed until they were reduced to a singularity. This process is incredibly slow, meaning the individual would die long before reaching the final, irreversible stage. Yet despite the apparent danger, black holes are so widespread that they cannot be ignored. In spite of the closest one being far away, the sheer number of them in our galaxy makes them an important topic for scientific research. In 2019, scientists reached a historic achievement by capturing the first clear image of a supermassive black hole at the center of the M87 galaxy. This image was taken over several nights, and with each exposure, the data was meticulously compiled to produce a better image and gain more insights. The most impressive finding was that a black hole isn't merely a single spaceless void, it consists of 3 distinct layers. 1. The event horizon, marking the point beyond which nothing can return. Once an object crosses this boundary, it will always gravitate toward the black hole. 2. The sphere of photons, where light is trapped in orbit. Any light that enters this region is caught and cannot escape the black hole's gravitational hold. 3. The singularity, where matter is compressed into a single point in spacetime, creating a region where the laws of physics as we know them no longer apply. This dissection of physics's rules is one of the many reasons studying black holes is so challenging and captivating. What's even more fascinating is that each black hole behaves differently. While they share a similar fundamental structure, each operates in its own unique way. Unlike other celestial objects that can be studied directly, black holes can only be examined indirectly. Scientists rely on observing the radiation emitted by black holes and the surrounding gas and dust. Sending a probe is impossible. Anything that crosses the event horizon is pulled into the singularity, where it would be crushed into an infinitesimally small point. This limitation forces researchers to rely on two-dimensional models to study these three-dimensional objects. Furthermore, black holes come in various shapes and sizes, adding another layer of complexity to their study. Researchers have proposed several theories to explain how black holes form, with one of the most widely accepted being that they originate from collapsing stars. When a star runs out of fuel, it can no longer generate the energy needed to counterbalance the force of gravity, causing it to implode. If the star is sufficiently massive, this collapse continues until the star becomes a singularity. NASA researchers have focused on a particularly powerful galaxy, M87, where they observed a massive whirlpool of hydrogen gas rotating at an amazing speed of 1.2 million meters per hour. Despite the extreme forces at play, the gas didn't fly apart, leading scientists to deduce that there must be a massive object at the galaxy's center holding it all together. This object turned out to be a black hole with a mass billions of times that of the Sun. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to model rotating black holes. Kerr's theory proposed that instead of collapsing into a singular point, a rotating black hole could form a ring of fire, or an accretion disk. This disk would rotate so quickly that the outward forces would counterbalance the gravitational collapse. Kerr's work also brought about the concept of the Einstein-Rosen bridge, or wormhole. A wormhole is a hypothetical tunnel connecting two distant points in spacetime, potentially even linking parallel universes. The idea of wormholes has intrigued scientists for years. Some theories suggest that the formation of the universe itself might have involved processes similar to those found in black holes. One such idea is the possibility that our universe was born from a black hole in another universe, creating a chain of cosmic events that link multiple realities through space and time. As our instruments become more advanced, researchers are beginning to detect gravitational waves, ripples in spacetime caused by cataclysmic events such as the collision of two black holes. These discoveries have opened up an entirely new way of observing the universe, known as gravitational wave astronomy. This emerging field allows scientists to listen to cosmic events that were previously undetectable, offering deeper insights into the nature of black holes and their interactions. Moreover, the Event Horizon Telescope (EHT) project continues to push the boundaries of observational astronomy. By coordinating a global network of radio telescopes, scientists are capturing ever-clearer images of black hole environments. These high-resolution snapshots not only confirm Einstein's predictions but also provide new puzzles, challenging current models of how matter behaves under extreme conditions. Despite these advances, countless questions remain. What lies beyond the singularity? Can black holes truly evaporate completely, leaving no trace behind? Is it possible to harness their energy, or would attempting to do so result in catastrophic consequences? One thing is certain: black holes are not merely distant cosmic curiosities. They are central to our understanding of the universe, its history, and its future. As science advances, what was once the stuff of science fiction is becoming an essential part of science fact. The more we learn, the more we realize how much remains to be discovered. Black holes continue to challenge the boundaries of human knowledge, compelling us to explore, question, and redefine what we believe to be possible. Conditions close to a black hole may provide information about how spacetime itself behaves. Additionally, if wormholes do exist, they may offer a mechanism for exploring extensive areas of space and time, making new possibilities for interstellar travel, although these ideas continue to be speculative. This motivates researchers to investigate the most profound questions about the nature of black holes in our universe. The subject has sparked significant fascination among scientists, and their research has advanced dramatically over the years. These enigmatic cosmic entities defy many of our conventional understandings of physics, particularly gravity. The fact that they remain nearly invisible makes them even more fascinating, prompting scientists to continue investigating their mysteries. With a keen interest in technological and theoretical advancements, our comprehension of black holes becomes deeper and more complex. It's clear that black holes are not only fascinating objects from outer space, but also serve as important components of the cosmic puzzle that might help unlock the mysteries of the universe. As we progress, comprehending black holes remains one of the most complex and fascinating topics in astrophysics. Their capacity to bend and warp spacetime itself gives them an extraordinary place in the study of cosmology. As we delve deeper into their secrets, we get closer to understanding the fundamental mechanics of the entire universe, including the nature of space-time and matter. The study of black holes offers insight into the way gravity interacts with quantum forces, opening new avenues of research that could one day provide answers to some of the deepest questions about the universe's fabric. One of the most important ongoing challenges for scientists is reconciling the theoretical differences between general relativity, which describes large-scale gravitational behavior, and quantum mechanics, which governs the subatomic world. Black holes, with their extreme circumstances, provide a unique laboratory for studying these forces side by side. They are some of the few locations throughout the universe where the effects of both quantum mechanics and gravity become apparent in ways that are hard to duplicate in a terrestrial setting. This duality makes black holes uniquely valuable to researchers working to develop a unified theory of physics that can encompass both of these primary forces. Attempts to comprehend black holes have led to several groundbreaking discoveries, one of the most notable being the detection of gravitational waves in spacetime. These ripples, first predicted by Einstein in the early 20th century, are brought on by the motion of enormous objects, such as the collision and merging of black holes. The first observation of these waves, confirmed in 2015, marked a new era in astrophysics, allowing scientists to study cosmic events that occurred beyond the reach of traditional observation methods. Gravitational wave astronomy has provided us with new ways to observe the universe, offering fresh perspectives on the behavior of black holes and their role in the cosmos. Despite all the progress made in the study of black holes, there is still a great deal to learn. As technology advances, so too does our ability to see the universe from new and more profound perspectives. The creation of more powerful telescopes, both on Earth and in space, has expanded our ability to observe distant black holes, revealing new details about their structure and behavior. Additionally, the development of advanced computational models and simulations has allowed scientists to model the complex dynamics of black holes and their environments with unprecedented accuracy. These tools will continue to enhance our understanding of these cosmic giants and their impact on the universe. Looking to the future, the continued study of black holes is expected to yield even more astonishing revelations. As we work to improve techniques for observation and push the boundaries of theoretical physics, we may uncover new aspects of black holes that challenge our most firmly established ideas about the nature of reality. The possibility of discovering new types of black holes, their function in galaxy formation, and exploring the relationship between black holes and the fundamental structure of spacetime are just a few of the thrilling avenues of research that lie ahead. In addition, black hole research is likely to have far-reaching implications for other science-related fields. Comprehending the extreme conditions near a black hole singularity may provide us with insights into the behavior of matter and energy under conditions that would otherwise be impossible to replicate. This could have applications not only in astrophysics, but also in fields like materials science, quantum computing, and the development of new technologies. Beyond scientific advancements, the exploration of black holes continues to captivate the imagination of people worldwide. The mystery of what lies beyond the event horizon, the ultimate fate of anything that crosses it, and the strange, often paradoxical nature of these objects continue to inspire a sense of wonder and curiosity. For many, the concept of black holes evokes images of cosmic adventure, leading to deeper philosophical inquiries into the nature of existence, time, and the universe itself. As we continue to explore black holes, we are reminded that our understanding of the universe is far from complete. These enigmatic objects challenge our most fundamental concepts of physics and offer a window into the deepest aspects of the cosmos. The journey to unlock their secrets is long, but each discovery brings us closer to understanding the fundamental forces that shape the universe. In conclusion, black holes are not merely astronomical oddities, but rather key players in the cosmic dance of the universe. They hold the capacity to answer some of the most profound questions about space-time and the foundations of reality. While we have made incredible progress, black holes remain a fascinating mystery. Our growing understanding of them continues to drive research and fuel the imagination of researchers and non-researchers alike. The ongoing investigation into these enigmatic entities will undoubtedly continue to produce novel and surprising insights, providing us with a deeper comprehension of the cosmos and our place within it. As we stand on the threshold of future discoveries, the study of black holes serves as a powerful reminder of both the vastness of the universe and the limits of human understanding. Each step forward in black hole research opens new doors, not only to scientific innovation but also to philosophical contemplation. What does it mean for time to slow near the event horizon? Could black holes be gateways to other universes? Might they hold clues about the very beginning of time? These questions, once relegated to the realm of science fiction, are now being explored in serious academic research. Concepts like Hawking radiation, black hole entropy, and information paradoxes challenge our existing models and push the boundaries of known science. The pursuit of answers requires collaboration across disciplines, from theoretical physics to astronomy, from mathematics to computer science. Moreover, black holes serve as cosmic anchors in the structure of galaxies, including our own Milky Way. At the center of most galaxies lies a supermassive black hole, millions or even billions of times the mass of our Sun. Understanding how these massive entities influence the birth, growth, and death of galaxies is key to unlocking the story of cosmic evolution. Public interest in black holes also reflects a broader cultural fascination. Images like the first-ever photograph of a black hole, released in 2019, captured global attention and underscored the power of collective scientific effort. It was a testament to decades of research, international collaboration, and the relentless curiosity that drives human progress. Looking ahead, upcoming space missions and observatories, such as the James Webb Space Telescope and next-generation gravitational wave detectors, promise to deepen our insight. These tools will allow scientists to peer further back in time, into the infancy of black holes and the early moments of the universe itself. In the end, black holes are more than just celestial phenomena. They are symbols of mystery, thresholds of knowledge, and mirrors reflecting the brilliance of human inquiry. Our journey to understand them will likely never be complete, but it is precisely this endless pursuit that defines the very essence of science.